Alright, welcome to this video. I want to practice working with AVL trees, in particular doing some of the rotations related to AVL trees. And to do so, at least to start out here, I'm going to work again with this sequence of random numbers that I generated in an earlier video. And again, I just want to add the numbers to an AVL tree in this order and try and maintain balance as we go. Now, we did take a look at these numbers earlier, and they already created a pretty balanced tree. So as we go, we might not encounter a lot of balance, but let's see what happens. Okay, so let's get started here. Our first node is going to be an 11, and it becomes the root. No imbalance there, no imbalance we could have there. The next node we're going to add is the 4. Again, this state is balanced. These first couple trees are in balance. We could definitely go ahead and calculate if we wanted. Our height here is 0, our balance factor is 0, our height here is 1, our balance factor is 0, but again, as I mentioned, for these early steps, it's pretty straightforward. We're going to get a 21 here. I had my balance factor of 0 there, that was wrong, but now it's 0. Here we're going to have a height of 0, balance factor 0. 25. Alright, again, height 0, balance factor 0. I guess we're getting into a little bit here. Now we might have to change our height and our balance factor on our nodes that are above, so let's just go ahead and do that. So new height 1, balance factor -1 minus 0 is -1, and this one height is going to be, looks like 2, balance factor is going to be 0, -1, -1. Okay, -1, -1, we're still balanced, so looks like we did the first row here, no problem. Let's try our 15. Okay, that's a greater, less than 15. Our balance factor becomes 0. So actually, as I mentioned, these random numbers are kind of, they cooperate kind of well. Let's see here. This one actually looks like it might be dangerous. So greater, less than 414. And here we'll start with height and balance factor of 0, and then recurse up here to fix the height and the balance factors above. So our height here, 1, balance factor is 0, minus 1 is 1, left heavy. Height and balance factor here, height is 2, balance factor is 1 minus 0 is 1. But now on our root node here, our height is going to be 3, our balance factor is 0 minus 2 minus 2. Okay, so we get some imbalance here. We need to fix it. And our imbalance tells us, -2 tells us we're in the right case. But looking to our right child, it's a positive one. That means we're right-left. So to do that, that means we need 2 rotations. We need to first fix the left part by doing a rotate right on my 21. So I'm going to just use my scratch over here. 11, 4. I'm going to do rotate right on my 21. The 15 is going to come up. The 21 comes down, and the 25 goes for the ride. Okay, so the 21, so the 15 comes up. The 14 goes for the ride, and we actually swap a child, but there's no child. It's a null child here. So we end up in this state. This is the middle. This is after fixing the left. So now we're in a right. So now we need to do a left rotation on this 11. So I'm going to do that and replace my original tree here. We're going to rotate left on the 11. So the 11 is going to come down, bringing the 4 along for the ride. The 15 becomes the new root. The 15 passes its left child over to the 11, but the 21 and the 24 come along for the ride. Now, there's only a couple nodes that we updated the references on here. Specifically on the 15 and the 14, we did an earlier rotation on the 21 as well, but because of those rotations, we now actually have to update the height and balance factors of those few nodes. I actually erased all the height and balance factors, so I'm going to quickly just redo all of them. Okay, and after updating the height and the balance factors, we notice that indeed our balance factor on the root node has returned to 0, so we're good. Okay, so all that happened as a result of trying to add the 14 there. Let's continue. Let's try and add the 1 now. So the 1, less than, less than, less than. Right, height and balance factor is 0 here. Let's recurse back up and fix them as we go. Okay, back up. Height is 1. Balance factor is 0. Minus and minus 1 is 1. Okay, back up. Height is 2. And we get 1 minus 0 is 1. We're okay. Up to the next level. Height is 3. We get 2 minus 1 is 1. We're still good. All right. After the 1, no imbalance created. Let's add the 9. Okay, recurse left, left, right. Okay, and let's recurse up and fix the balance factor, the height and the balance factor as we go up. So next level up, height is 1, balance factor 0 minus 0 is 0. Okay, we introduced balance there. Next level up, height 2, balance factor 1 minus 0 is 1. And top level here, height 3, balance factor is 2 minus 1 is 1. Still no imbalance. Good to go. Continuing with the 20. Greater than 15, less than 21. Getting lucky here, adding them into locations where they don't introduce imbalance. In fact, they fit well there. That made us a little more balanced. We can again verify as we go up by computing our new balance factors and our height. Here, our height is going to be 1. Well, it's already 1, but our balance factor, we introduced balance. Here, our height actually remains unchanged, 3. Our balance factor, 2 minus 1, still 1. Okay. Now we'll try and add a 2. So 15 is less than, so 2 is less than 15 rather, less than 11, less than 4, greater than 1. Okay, let's try this one again. Let's see, does this introduce imbalance for us? Okay, so again, a leaf node, height balance is 0. So next level up, we're going to get height of 1. Balance factor is minus 1 minus a 0. We get minus 1. No imbalance. Okay. Next level up, height is 2. Balance factor is going to be 1 minus 0 is 1. Okay. No imbalance. Next level up, our height's going to be 3. Our balance factor is going to be 2 minus 0 is 2. Okay, here we need to be careful now. That's imbalance. And notice, if we miss this, we can keep going up, we get imbalance up here as well. But if we're lucky, if we can fix the imbalance down here on this node, then maybe we won't get imbalance up above here. And let's see if that's the case. So here we've got imbalance of 2. That means we're left balanced because it's positive. We look at our left child. It's got a balance factor that's also positive. So we must be in a left-left situation. That means we need a right rotation on our 11 here. So again, I'm going to do a little bit of jotting of notes down on the side here. My 11's coming down with the 14 for the ride. So these two come down. And then the 4 is going to come up and become my new root. The 9 gets swapped over to the other side, and the 1 and the 2 just come up for the ride. Okay, so let's be careful here. My 14 is coming down. It's coming down with the 11. Now the 11, I'm going to have to fix its height and balance factor after we're done. But the 4 is coming up. I'm actually just going to do this. The 9, remember, gets passed. So boom, the 9 just swapped over to that other side. Now the 4, yeah, it goes something like that. Okay. All right, now my 2 got down here. I'm going to move my 2 back over just to make it a little bit easier. But the reason I kind of moved it up and down like that is to show you that that's actually what happens in the code. This little complex here, this 1 and this 2 that we moved up here, we didn't have to change any of its values. Those values stayed the same. Now the actual height and balance factor on 4 might have changed, and also on the 11. So those are the ones we want to update. So now, after doing the swap business, all the rest of these should be correct, but now we need to update our height and our balance factor on these two nodes. So this one's going to be 1 and 0, it looks like. And this one now is going to be height, it looks like 2, and balance factor also 0. And again, remember, we were in the middle of fixing the balance factors all the way up. Let's go up to the top now. My height is 3, my balance factor is still 1. So by fixing the imbalance that we had in this lower subtree, it actually solves the imbalance up above that we were introducing as well. All right, that was the 2. Let's try the 17. See if we can get away with this here. Okay, we're getting in a little bit of messy territory. So I'm just gonna say I've got a 17 over here. Okay, once again going back up, we get then the height is 1. My balance factor looks like this is a left child here, in case that's not clear. Left child is height 0 minus 1 is a 1. Next one up, height 2, we got 1 minus 0 is 1. Next level up, height 3, 2 minus 2, 0. Okay, 26, it's going to go psh, psh. Okay, let's recurse our way back up on this one too. Recursing back up, we have here height 1, balance factor minus 1, minus 0, minus 1. Next one up, we get height of 2, balance factor 1 minus 1 is 0. Next level up, height 3, 2 minus 2, 0. Okay, continuing on, my 13. Looks like less than, greater than, ooh, less than, 13. Right, recursing back up. Height here looks like it's 1. Balance factor is 0 minus a minus 1 is 1. Okay, next level up, height 2. Balance factor is going to be 0 minus 1, minus 1. Next level up, height looks like 3. Balance factor is going to be 1 minus 2 is minus 1. And top level here, height is now 4. My balance factor is going to be 3 minus 2, 1. Still no imbalance. Getting pretty lucky without too many rotations here. Let's continue. 7, less than, greater than a 4, less than, and a less than. Again, height 0, balance factor 0. Let's recurse our way back up then. So 0, 0 here, that's going to give us a height of 1, and it looks like 0 minus a minus 1 is 1. Next level up, height 1, 1, that's going to give us height 2, and balance factor 0. Next level up, height 1, 2, so our new height is 3, and our height minus height is, it looks like, minus 1. And up to the top level, still 4, and 3 minus 2 is still 1. So again, even though we're updating them, these last two didn't change, we're still updating them every time if we can. A 24, which looks like I made an error. So if that one was a 25 from above, that looks right. And this is a 24, which we would add here. And again, height 0, balance factor 0, moving on up. Let's do a quick recurse. We get what? Height 1 and balance factor 0. Next level up, it's looks like height 1, 1, 1, so our height is 2, balance factor 0. Next level up, our height is 3, 2, it looks like it's 4, and we're still at 1. Still haven't upset that one. Last chance, I guess, 30. We get a 15 greater, 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 greater. We know our 30 is the largest one here. And let's just, again, recurse our way up. So looks like 1 and minus 1 minus 0 is minus 1. It looks like our height here is 2, and 0 minus 1 is minus 1. Looks like our height here is 3, and we got 1 minus 2 is minus 1. Lots of right heavy here after adding that 30, but finally our height here is 4. That actually balanced us out a little bit here, because now we get 3 minus 3 is 0. Okay, only a couple rotations for this data, and part of the reason for that is that this data that we had here was already kind of in a nice balanced order. And we saw that in our earlier video when we put it into just a naive binary search tree without doing the reordering as we went. Now, this was just meant to work with some random data and practice working with our AVL trees, but I also wanted to demonstrate a little bit of why AVL trees are useful for us by looking at just another sequence of data that we could add. And this is just numbers coming in order. So maybe I'll just start as an aside here. We know that in a normal binary search tree, putting the numbers in order is actually a painful thing to do because you end up with this binary search tree, which of course is not a binary search tree at all. Well, it is. It's just I call it a stick or a branch. It doesn't have any of the beneficial parts of the binary search tree, which is making it an efficient search. It reduces our search, unfortunately, to order n because the depth will be n. But an AVL tree is supposed to fix this. It shouldn't give us a shape like this. So let's see what happens. So if we put in our AVL tree, we're going to get our 1. We're going to get our 2. But as soon as we get our 3, this is actually out of balance on the 1. This is our first right. And the order I'm going to be putting this in, we're going to get a lot of rights, probably all rights. But we can see after this step, if we do the rotate left on the root node, we end up with this tree. And this tree is perfectly balanced. And we can continue on that tree, adding a 4, and maybe a 5. And now that 5 introduces imbalance here on the 3. Okay, let's continue then. So continuing, we could add now a 6. We'll now notice that the 6 now adds imbalance, not on the 4, but on the 2. So that actually causes us, again, we're still in right, to do a rotate left here. The 4 comes up, the 3 gets passed along, and the 5 and the 6 here. Let's do one more just to see what happens, because when we add the 7 here, we get imbalance on these 3, and we get 5, 6, 7. So whereas we had a tree over here that went to 7 looking like this, after 7 we're actually perfectly balanced. Now along the way we aren't always perfectly balanced, but we do kind of maintain this balance. Now of course if we keep adding on the right, we should expect we'll likely get right heavy cases. So again, we get another case here, 8, right heavy, another case here, right heavy. With the first 8 nothing happened, no imbalance happened, but with the 9 we now get imbalance. And maybe take a moment, pause, think to yourself, where's the imbalance here? What's the correct operation to fix it? Okay, and you know, if you like, go and do the next couple numbers and see if you can follow along. So the imbalance was on the 7, so we actually get this node, this structure here, again back to balance now. Okay, I'm not calculating the balance factors, I'm just sort of doing it in my head. I'm just doing left minus right here. You can kind of visually just look and see. You were looking for differences more than one. Okay, if we get a 10 here, again, one difference, but here we have 2 difference. So it looks like imbalance on the 6. So let's try and rebuild that whole one. I'm going to sketch it over here. The 6 is going down with the 5. The 8's coming up. It looks like the 7 and the 9 and the 10. Should be a 9. So let's replace that over here. We get an 8, 6, 5, 7, 9, 10. And maybe we can see here that, again, that fixing that imbalance makes the 4 still off by 1, which is fine, as long as we don't get higher, more depth here. And we see again 11 here causes imbalance on the 9. It does cause imbalance on the 4, but by fixing it on the 9, we'll fix it on the 4 as well. So we get 10, 9, 11. But now, when we put the 12 on, this shape here is so balanced, there's nothing we can do to that one, that even the 8 is balanced, but the 4 is not. So now we'll do one final last. No, this is the last one maybe I'll do here, just because we could do this for hours, but we're just, you know, hopefully this is enough for our, get some experience. We're going to rotate left on our 4, so the 4 is going to come down, The 2 and the 3 and the 1 all go for the ride. Okay, we need to be very careful here, and I probably should have left a little more room. The 8's coming up, but the 6, the 5, and the 7 get passed over. On the right-hand side, it looks like we get our 10, our 9, our 11, and our 12. Okay, maybe just as a little bit of extra practice for you, take this to 15, because 15 is the next perfectly balanced state we should get. So see if we get ourselves in a perfectly balanced state. Okay. But add those next ones in, see what you get. You'll probably do a few more rotations over here. If you've been following along and doing these rotations for both my examples and you feel pretty comfortable with them, then you'll probably understand the AVL rotation pretty well. The good way to practice it is just generate some random numbers for yourself and start inserting them into a tree and do the rotations until you feel very comfortable with them. All right, so this is one binary search tree that balances itself, an AVL tree. In my next video, I'm going to introduce a red-black tree, which is another self-balancing binary search tree. All right, thanks for watching, and we'll see you in the next video.